In the Michaelis-Menten model to describe the velocity of many enzymes, the enzyme-substrate complex is a necessary intermediate between substrate and product. So we will start with the reaction scheme as follows. So first we have enzyme plus substrate. And this can associate, form into the enzyme-substrate complex, which can then dissociate after the enzyme works into enzyme and product. So how do we get the Michaelis-Menten equation out of this? First thing you have to do is assume a few things. So in order to continue to derive the equation from this scheme, a few assumptions must be made. First is the steady state assumption. This assumption states that the formation of ES complex is equal to the rate of dissociation from the ES complex. This can be written in the following equation. So first we have to label these. We have K1 here, K negative 1. So association, dissociation, formation I should say, and then we have dissociation from ES to E and P, which is this K2. So we can write this steady state assumption as this equation. K1 times E times S, substrate concentration, is equal to, so we're saying that's a steady state. The formation is equal to the dissociation. This side, K negative 1, enzyme substrate concentration complex, plus the K2, so from enzyme substrate to enzyme product. Okay. Another important idea to understand in this equation is the total amount of enzyme, or ET. Total of enzymes would be equal to the free enzyme plus the enzyme substrate. So free enzyme plus enzyme substrate. So we can write that like this. Enzyme total is equal to enzyme substrate complex plus free enzyme. If I solve for the free enzyme, so getting E by itself by subtracting, subtracting it out, here's what you would get. So subtract this from this equation, here's what you get. Free enzyme, or enzyme, equals enzyme total minus enzyme substrate complex. Okay, now let's go back to this equation and plug in this whole concept here. So that's going to look like this. I have to get a little more complex before I can simplify this. So we have, back to here, K1. Now I'm taking this and adding it in to the other equation. So parentheses here, enzyme total minus enzyme substrate times substrate concentration equal to, this is the dissociation side, K negative 1, enzyme substrate complex plus K2, enzyme substrate. Okay, so we have, now let's use our algebraic properties to simplify this equation a little bit. First half, we distribute the K1 and the S. Let's see here. Right side we can factor out this ES. So simplified, the equation looks a little something like this. K1 times enzyme total times substrate concentration. So we're distributing these things there. Okay. So minus, again, we have K1 enzyme substrate now times substrate concentration is equal to enzyme substrate. Make sure we're recording still. Okay. Enzyme substrate. Okay, so we factored these, and it's going to be distributed later on. So hopefully this is looking like something we're going to use later. And yes, it is. K negative 1 plus K2. Okay. Now we see that on the right side of the equation we have the numerator. This here is the numerator of the Michaelis constant equation, which is this. Michaelis constant, or Km, is equal to, what is it? It's K negative 1 plus, here we go, plus K2, and this is all divided by K1. Okay. So how do we replace this with Km in this equation here? So let's try to isolate that. So we can simplify the terms and just use Km. To do that, we need to divide out the K1 from the left side. So the equation looks like this. Once we divide that out, we simplify this to say Km. Again, that's the Michaelis constant. So this is the equation now. Enzyme total times substrate concentration minus enzyme substrate times substrate concentration equals, now we have enzyme substrate and Michaelis constant here. Okay, subtract over the ES and S. Let's do some factoring, and here's what we get next. So, yep. Is this visible? Yeah, it looks pretty visible. Enzyme total, substrate concentration equals enzyme substrate Km plus substrate. Okay. Now if we know what the end goal is, this looks pretty darn close to it. We already have the denominator of the whole equation right there. So we're going to get to that somehow pretty soon. So to try to get the ES by itself to resemble a portion of the next assumption is the next goal, which is referring to the V naught, or what we want to actually solve for in the Michaelis-Menten equation, which is velocity of the enzyme catabolism. So the assumption is that V naught is equal to K2 times the enzyme substrate, or also enzyme substrate is equal to VO over, so we just switch these things around, divide this over K2. Okay. So the equation after getting ES by itself looks like this. So we can plug this idea into the enzyme substrate. Let's look at this. So we have to divide everything by this. Okay, Km plus S. So we're dividing this side also by Km plus S. Gives us this equation. Enzyme substrate equals enzyme total times substrate, all this over Km, Michaelis constant plus substrate concentration. Getting close, getting very close. Now I can plug the concept here, the V naught over K2 into the equation, which is going to look like this. So all we're doing is taking this out, replacing it with these other facts, these other assumptions. So it's going to look like this. So we have VO over K2 equals enzyme total times substrate concentration divided by Michaelis constant plus substrate concentration. Okay, so these are the assumptions that we've been working with. Michaelis constant, V naught is equal to these things. The steady state assumption as well. The last assumption, the last fact that we need to work with is that of Vmax. Vmax. So the assumption of Vmax is equal to K2 times enzyme total, which we have conveniently, let's say, well, first we have to get the VO by itself. I'm jumping ahead of myself. We have to multiply by the reciprocal here, K2 over 1. Okay, so we're going to multiply that over, getting VO by itself over there. It's going to read like this. K2, again, this is referring to this dissociation. K2 times enzyme total times substrate concentration. Okay, this is going to be all over Km plus substrate concentration. Okay, now, like I said earlier, where was I with the Vmax equals K2 times enzyme total. We have that right here. So the assumption, so we have that conveniently isolated here again, the numerator. So plug in the term Vmax into the equation, and it reads like so. VO, so this is the velocity we're trying to get. This is what we're trying to see in enzyme kinetics, is the velocity at which they can catalyze the substrates. So VO equals Vmax, okay, times substrate concentration over Km plus substrate concentration. This right here is the Michaelis-Menten equation.